AB Calc 4.2, day number 2, concavity and inflection points, as well as the second derivative test. Our objectives are to know and apply the first derivative test, which is review for us. We did that in our last lesson. Use the second derivative for concavity and points of inflection, and then know and apply this thing called the second derivative test. All right, so class opener. State the Max Min Existence Theorem. Include the conditions that must be met to use this theorem. So the Max Min Existence Theorem says that if a function f of x is continuous, there's our first requirement, on a closed interval, right, from a to b, let's say, there's our second requirement, then f of x will attain a maximum and minimum value. Okay, so will attain. All right, so if we have continuity on a closed interval, a function must attain an absolute max value on that interval, as well as an absolute min value. Now, it could also attain some local maximum and minimum values as well. But if either of these criteria are not present, this process becomes a lot more complex. To answer our review question below, if there isn't a closed interval or a continuous function, for that matter, how are we going to determine if the function ever achieves a max or min value? Well, then we have to dig into it a little bit more and have to look at what does the function look like on that interval. Okay, there's no guarantees at all. Just need to make sure we are able to diagnose the situation through observing it graphically. Okay, so let's talk about the first derivative test, something that is review at this point. Scenario 1 would be that f of x has a local maximum at an x value of c. That happens at a critical point c, where f prime of c is either 0 or does not exist. If f prime changes from positive to negative at that value, then f has a local maximum. The second scenario would be a local minimum at x equals c, very similar, except f prime changes from negative to positive at that value. And then, of course, the third scenario is if f prime doesn't change sign at that critical value c. This would be no extreme value present. Okay, let's talk about the second derivative a little bit, and specifically about concavity and points of inflection. So if f double prime is greater than 0, then f of x, or the function f, is concave up. Okay, so what that means for f prime is that if f double prime is greater than 0, then f prime is increasing. We're going to look at an example of this in a couple of minutes. Whoa. If f double prime is less than 0, then f is concave down. What does this mean about f prime? Well, if f double prime is less than 0, then f prime is decreasing. The big takeaway, though, from these first two questions is that f double prime connects to the concavity of f. Okay, so in points of inflection are very similarly related to f double prime in the way that local mins and maxes are related to f prime. So for example, when f double prime of x equals 0 and changes sign, then a point of inflection is present. F of x has a point of inflection. Now, this is also true as well if f double prime doesn't exist. Okay, so if either of those two are true, right, really I'm just finding critical values for f double prime, right? Instead of f prime like I did with local min and max values. Okay, now I'm not concerned at all with changing sign, whether we go from a positive to a negative or a negative to a positive. That has no effect on whether or not we have a point of inflection. So that's different than if we were looking for local extrema using f prime. Okay, so this has no bearing on whether or not a point of inflection is present. All right, let's look at a couple of examples. All right, so let's consider these two graphs, one of which is f of x, which is a cubic. Its second derivative would be linear. Okay, so its first derivative would be quadratic. Its second derivative would be linear. Notice where f double prime equals 0. At this value, f double prime at, let's call this c, is equal to 0. Okay, we're going to consider that in just a moment. First, let's answer the questions below. Okay, so at the max value of f, let's find a local maximum value. So let's call this value x equals, let's just say it's -3. So at x equals -3, f of x has a maximum. Notice that f double prime at -3 is less than 0. Okay. Now, why would it be less than 0 there? Well, f of x is concave down. At that point. Now, not shown right now is f prime of x. What would f prime of x be at x equals -3? Okay, f prime at x equals -3 would actually equal 0. So we're starting to develop what's called the second derivative test. You'll see that in a moment. Okay, a minimum value for f. Well, that would happen right about here. Let's say that that's x equals 1/4. Okay, I'm estimating clearly. Well, f double prime at 1/4 happens to be greater than 0. Look at it right here. It's about 9. Okay, why would it be? That's because f of x is concave up at that point. Okay, so if I were to consider f prime at 1/4, that would also be 0, right? The slope of the tangent line at both that min value at 1/4 and max value at x equals -3 would both be 0. Now, let's consider for a moment this value here, this value c, right? Let's say this is x equals c. I'm not going to try to estimate that. Notice the second derivative is 0. Look at this point and tell me what's unique. Yeah, like you're going to tell me. But what you'll notice is unique is that the concavity, right? The concavity of f of x changes at x equals c. What that means is that f double prime of x changes sign. We notice that at x equals c. And formally, we say that f double prime changes sign at x equals c, and it equals 0, right? F double prime at c equals 0 and changes sign. Therefore, f of x has a point of inflection. It's not well spaced there. I'm running out of space, so deal with it. F of x has a point of inflection at x equals c. Cool. Let's continue with some more on this topic. So with that, I want you to consider what I talked about up here, this max value and min value. We're going to talk about the second derivative test. Okay, now, notice that f prime at what we said, -3, and at 1/4 equals 0. The second derivative test is used when f prime at c, or at some value, is equal to 0, and the second derivative is either positive or negative. So instead of taking the first derivative test and determining did the first derivative change sign, what we can do is we can actually just determine whether or not we have a max or a min based on that the slope of the tangent line to the original function is 0, and that the concavity of the function is greater than 0 or less than 0 by looking at the second derivative. So let's look at two examples. Let's look at example 1 here. Okay, so example 1 says if f prime at c is 0 and f double prime is less than 0, then there's a local max at x equals c. Let's look at that. Here's x equals c. Looks like f prime at c equals 0. Okay, and you can tell by the concavity, of course this is the graph of f of x. You can tell by the concavity, just by the shape at that point, right, that f double prime at c would be less than 0. Okay, therefore, at this value, x equals c, okay, at x equals c, there'd be a local max. Okay, likewise, the other way around, looking at example 2, f prime at c equals 0. Let's sketch a very similar graph. Okay, there's x equals c. At this value, there's a local minimum, and the reason why is because f prime at that value, okay, f prime at c is equal to 0, and you can tell that the concavity of the graph at that point would be greater than 0. Okay, thus, at x equals c, there is a local minimum. Okay, now we only have to test f double prime at the value for c. All right, please be aware of that. No need to test it on an interval. We're just testing it at the value. Okay, let's continue. All right, here we are, example 1, using f prime and f double prime to graph f. Here we've got f prime. Identify where any local extrema of f occur. So recall that we want to determine where f prime equals 0 or doesn't exist. Well, this is a polynomial, so it'll always exist. So I'm going to set 4x cubed minus 12x squared equal to 0. Factor out an x squared. And let's plot a 4 while we're at it. We get x minus 3. Now, if I were to graph f prime, I would have zeros at x equals 0 and x equals 3. All right, but be careful when you do a quick sketch of this. You could test intervals around this. I know that the end behavior of a cubic with a positive leading coefficient should look like that. I know it'll look like this. But since I have an x squared here, that means my function will bounce off. Will bounce off x equals 0. Therefore, I'm going to have only one local extrema. My dog is seriously bothering me right now. Drinking water and whining. One local extrema at x equals 3. Now classify that local extrema. Now if we're looking at the graph of f prime is less than 0 on this interval, and then greater than 0 on this interval. So since f prime at 3 equals 0, and changes from negative to positive, then f of x has a local minimum at x equals 3. That's a 3. All right, there's no local minimum or maximum here because f prime doesn't change sign. F prime has 0 there, but doesn't change sign. All right, part B, find the intervals on which f is increasing and the interval or intervals on which f is decreasing. Okay, so f of x is increasing on the interval given, okay, when x is greater than 3, right? I can see that above in green. Now I'm going to trace where f prime is also less than in blue. Therefore, f of x is decreasing on the interval from negative infinity to 0, unioned with 0 to 3. Okay, and this is because, right, f prime of x is greater than 0 on the green interval, and f prime of x is less than 0 on the blue interval. Okay, find where the graph of f is concave up and where it's concave down. Find the points of inflection. So I'm going to do almost the exact same thing, except now I'm going to use the second derivative. So let's find the second derivative with respect to x. That'll be 12x squared minus 24x. Okay, so I'm going to do the same process, very similar, right? I'm going to find those critical values, find where the second derivative changes sign, and I'll have my point or points of inflection. Okay, so let's set this equal to 0. This will clearly always exist for all values. Let's factor out a 12x, and we get x minus 2. Okay, so now I know that f double prime at 0 equals 0, and f double prime at 2 equals 0. I'm going to sketch f double prime of x. Let's go in green. And it looks like it'll be a quadratic passing through at x equals 0 and x equals 2. Okay, and it's going to open up with a positive leading coefficient. So let's graph f double prime. Looks kind of like that. Not my best sketch, but it'll work. Clearly, I can see that f double prime equals 0 at those values. Already determined those. Thus, I can say that f of x is concave down on the interval from 0 to 2. That's because f double prime of x is less than 0. I can say f of x is concave up on the interval from negative infinity to 0 and from 2 to infinity. That's because f double prime of x is greater than 0. Now I can say that there's points of inflection on f at the following values: x equals 0 and x equals 2. And that is because f double prime of x equals 0, and don't have to be specific, but it changes sign. I spelled it right this time. All right, so let's go ahead and let's graph a possible functions graph for f. All right, so let me consider a few items. First of all, I know that there's a local extreme value, okay, a local minimum value at x equals 3. All right, so I know the graph is gonna do something kind of like that at x equals 3. I know that the function itself, f of x, is increasing only from 3 to infinity. So I'm pretty certain that that's going to happen. Now that could look different. Okay, it could waver a little bit in how it increases, whether it increases at a faster rate or something like that. That's fine. Okay, I know that there is 2 points of inflection. point of inflection at x equals 2. Okay, so that means concavity is going to change. Okay, we'll look at that in just a moment. And I know that there's a point of inflection at x equals 0. So concavity is going to change at x equals 0, and let's go here at x equals 2. Okay, so since my function is concave up at this local min, I'm going to make my graph change concavity from concave up to concave down. So you can see on this red interval, concave down, and then we make a swap to concave up. And the function is concave up after x equals 2. You can see that up here. Right? So I know concave up to the right of 2 as well as to the left of 0. Concave up, concave down in between 0 and 2. So my concavity to the left of 0 is going to be concave up. Now, there is no local extreme value at x equals 0. Right? It's not a max or a min, but it is a point of inflection. So I know that my graph after this point will be concave up. So here's a possible. And this green and red here is just labeling concavity, right? Concave up in green, concave down in red. Point of inflection here in blue, and local minimum value in yellow. Okay, that is a possible graph of f. Let's look at some more examples. All right, got another polynomial on our hands here in example 2. It says find increasing, decreasing, concave up, concave down, and inflection points. So increasing, decreasing, I'm just going to do with f prime. Since f prime will exist for all values and f double prime will exist for all values due to the fact that we're working with a polynomial, we don't have to worry about the derivative not existing. So f prime will be 12x squared minus 6x. I'm going to determine where f prime is equal to 0 by first factoring. Pull out a 6x, leave in a 2x minus 1. It looks like f prime at 0 equals 0, and f prime at 1/2 will equal 0. Okay, so I've got critical values at x equals 0 and 1/2. Let's sketch those real quick. Of course, f prime is a quadratic. It's going to open upward with that positive leading coefficient. Here's a x equals 0. Here's an x equals 1/2. General sketch of f prime opens upward just like this. Okay, so I can say that f of x is increasing on the interval negative infinity to 0, as well as 1/2 to infinity. I can tell because f prime of x is greater than 0 on that interval. All right, f of x is decreasing on the complement of that set, which would be 0 to 1/2. Okay, it doesn't ask us for local extrema, but I would just, of course, make the observation just for the extra practice to show that there is a local max at x equals 0. You can see that f prime equals 0 there and changes from positive to negative, and a local minimum at x equals 1/2. Okay, f prime at that value equals 0 and changes from negative to positive. All right, let's consider the second derivative for concavity. So the second derivative will be 24x minus 6. Let's set that equal to 0. That clearly will exist for all values. It looks like x would have to equal, oh, what was that? This would equal 0 when x equals 1/4. Okay, let's sketch a graph of f double prime, of course, which is linear. Okay, let's put a quick sketch here. 24x minus 6. Well, it's going to equal 0. That was sloppy. Let me try that again. It's going to equal 0 here at x equals 1/4. Now, a line with a positive slope that goes through the x-axis at that point would look like this. Clearly, concave down, concave up. And we'd have a point of inflection there at x equals 1/4. So f of x is concave down on the interval from negative infinity to 1/4, since f double prime of x is less than 0, and f of x is concave up on the interval from 1/4 up to infinity for the opposite reason. Okay, there's a point of inflection at x equals 1/4, since f double prime of x equals, actually I should say f double prime of 1/4 equals 0, and f double prime of x changes sign at x equals 1/4. Okay, cool. We justified our response, so if you're ever curious, like how do you justify your response? Well, here are our justifications. I didn't put a justification on the Max Min. That wasn't really part of the problem, but I've got justifications all the way through. All right, right on. Let's look at one more example. Pardon me, 2 more examples. Okay, so example number 3. We've got a function, y equals 3x to the 5th minus 10x to the 4th, and we're asked for points of inflection. So I'm going to find y prime first, and then y double prime. So it'll be 15x to the 4th minus 40x cubed. Second derivative, of course, which relates to the points of inflection, would be 60x cubed minus 120x squared. I'm going to factor this, taking out a GCF, greatest common factor of 60x squared. That leaves me with x minus 2. Okay, I'm going to make a general, no, I won't do that yet. Let's do this. Let's graph this thing, right? We want to know where y double prime is equal to 0 and changes sign. All right, let's make that work here. So let's set this equal to 0. Clearly, this would equal 0 when x equals 0 and x equals 2. So let's graph the second derivative, y double prime. Okay, here's y double prime. Of course, if you look at the derivative, it's a quartic 4th degree, right? And a 4th degree, you can see the degree there, and a positive leading coefficient will result in some movement here, right? Some end behavior that would look like, I don't know why I said movement. I was thinking ahead at what's going to happen at one of those zeros. Okay. I'm sorry. I want 3rd degree. Sorry. I was looking at the first derivative. Don't do that. Look at the second derivative. So it's 3rd degree. So its end behavior will not look like that. It will look like this. Okay, so I've got zeros at x equals 0 and at x equals 2. Now I'm strategically placing these values. You'll see why in a second. I've got a 2nd degree 0, right? So that means my function, which has end behavior like this, for the second derivative is going to bounce off there and pass through there. Okay, now, I could be done with this question right now. I can tell you right now that there's a point of inflection here at x equals 2. Why? Because f double prime at 2 is equal to 0 and changes sign, right? And I get a change in sign. Now, f double prime is also equal to 0 at x equals 0. However, there's no change in sign. So there's no point of inflection at x equals 0. Okay, so right now I know my answer is going to be E. However, I would have to, confirm that y of 2 is equal to negative 64. If I plugged in a 2, that would be 3 times 2 to the 5th, which is 32, minus 10 times 2 to the 4th. Let's see, what is that? 2 to the 4th would be 16. So this would be 96 minus 160, which is negative 64. So there you go. Your answer for example 3 is E. Let's look at example 4. F of x is x squared plus 1 over e to the x. Go figure, we're going to have to do a little quotient rule here. It's asking then for the graph of f and where it's decreasing and concave down. So I'm going to look at f prime. I want to know where it's decreasing, so I want to know where f prime is less than 0. So let's find f prime. That's low d high minus high d low over low low, or low squared. Okay, let me do a quick cool simplification. So you got an e to the x in both terms in the numerator, and I have an e to the x in the denominator. Technically speaking, I have e to the x times e to the x. So watch this. E to the x times e to the x. Now, because I have e to the x in both terms in the numerator, as well as at least one of them in the denominator, I can rewrite this as 2x minus x squared plus 1 all over e to the x. So I reduced. In essence, I factored out and reduced one of the e to the x's. Right, I got rid of that one by factoring them all out, reducing it out. Okay, so f prime is going to equal negative x squared plus 2x minus 1 over e to the x. All right, so I need to know, first of all, where f prime of x equals 0, and then I can test around that. So f prime of x will equal 0 when its numerator is equal to 0. I don't really care about its denominator, 1, because it will never equal 0, and 2, because it doesn't affect when the numerator will equal 0. Okay, so I'm going to solve this. Now I'm going to multiply everything by negative 1. And I'm going to factor. That ends up being x minus 1 squared. Okay, now this is true. This is true only when x equals 1. Okay, so when x equals 1, f prime, so f prime at 1 is 0. Let's graph f prime and see where f of x is decreasing. So at x equals 1, we've got a 0. Again, this is the graph of f prime. Okay, look at f prime. This is what f prime is. It's this thing. Okay, that's what f prime is. Well, actually, it's this thing, right? However, if I plug a negative or a positive number in for the denominator, it will matter, right? So f prime equals 0 at x equals 1. Let's plug in one value. We know that if I plug in x equals 0 or x equals 2, that will expose what the function will be doing on both sides, what f prime's output will be. So if I plug in a 0, okay, if I plug in a 0, f prime at 0 is going to equal negative 1 over 1. So I know that f of x is decreasing from negative infinity to 1. F of x is decreasing on the interval from negative infinity up to 1. All right, let's just see what's happening to the right. Let's do f prime at 2. Okay, f prime at 2 would be, oh gosh, let's see. That would be negative 4 plus 4 minus 1 over e squared. Okay, so f prime at 2 also comes out to be negative. So the function is decreasing everywhere except for at x equals 1. Okay, so I'm going to add that to this interval. Now we need to consider the second derivative. We want to know where the function is concave down. So I'm going to take the derivative of f prime, getting me f double prime. Got to use the quotient rule again. Okay, so that's low d high minus high d low. Derivative of e to the x is very nice. Over low low. Now I'm going to rewrite it in the exact same way I did earlier. And I'm going to reduce out one of those e to the x's. So our second derivative, let's compress that numerator. That'll be x squared. It'll be negative 2x minus 2x, which would be negative 4x. And that'll be 2 minus a negative 1, which will be plus 3. Now in a very similar way, I'm going to find out where f double prime is equal to 0. Now all that I care about again is the numerator. And I can easily factor showing me that f double prime at 3 and f double prime at 1 are equal to 0. Let's sketch f double prime. Let's do it in, we're not going to sketch it, we're going to test values. Let's test values around x equals 1 and x equals 3. Okay, so second derivative. Let's test these values. We're going to test, let's test x equals 0. We'll test x equals 2. We'll test x equals 5. Okay, let's do that. So f double prime of 0. If I plug in a 0, I get 3 over 1, which is 3. So I see I get positive second derivative on that interval. The function would not be concave down there. How about f double prime at 2? Well, f double prime at 2 would be negative 1 over e squared. Negative 1 over e squared. That'll be negative. Concave down there. Let's plug in a 5. F double prime at 5 would be 25 minus 20, which is 5, plus 3, which is 8 over e to the 5th. 8 over e to the 5th, of course, will be positive. So f of x, let's do it right here, is concave down on this interval from 1 to 3. So if I overlap these two intervals, right, if I overlap negative infinity to 1, 1 to infinity, with 1 to 3, I actually end up just getting the interval from 1 to 3, where both the function is decreasing and concave down. All right, guys, hope that made sense. We'll see you in the next video. Let your teacher know if you got any questions.